So, Professor, and we will just wait 2, 3 more minutes so that the more participant can join, right?
Yes, sir. Yes, sir.
Then
No
we will. Okay.
Rajesh, am I audible?
You are audible, but
but sound is little bit slow.
Sure. So, Professor, now we can start. The 30 participants remaining, they may join in between, right?
Yes, sir. Yes, sir. I'm okay with it.
Okay, just a minute. So, good evening, one and all. Now we are going to start the first session of the third day. So, at the onset, I would like to welcome Dr. P. Padam Girishan. He is the speaker for the today's session. So, Dr. Padam Girishan obtained MTech in Electrical Engineering from NIT Warangal, Ph.D. in Electrical and Electronics Engineering from NIT Trichy. Presently, he is working as an assistant professor in the Department of Electrical Engineering at NIT Agartala. Before joining the NIT Agartala, he worked as a research fellow in mechanical engineering science at University of Surrey, UK. His research interests are energy management control systems for electric and hybrid vehicle and renewable energy. So these are not limited to, these are the main research focus. With this brief intro, I would like to request to Dr. Padam Girishan to start the session.
Yes, sir. Thank you very much, sir, for the introduction. And before starting the session, I would like to thank the coordinator of this workshop, Dr. Arvind Jain, sir, and Dr. Bikram Das, sir, for inviting me to share my and giving me an opportunity to share my ideas and knowledge that I have in this field. Also, I would like to thank our my present organization, NIT Agartala, for permitting me to give this workshop and providing the resources for this. So with this, let me start the session. Let me just share my screen. Okay, sir, I hope the screen is visible.
Quite visible, quite visible.
Yes, yes. Thank you, sir, for the acknowledgement. So in this session, the session is actually divided into two parts. In the first session, we'll be discussing about the introduction to electric vehicles, and in second section, I'm going to discuss about the electric vehicle charging technologies. So this part is more important for as far as this FTP is concerned, because right now we can see there is a larger protrusion of electric vehicles into the market, and because of this, there is a great power demand that is going to arise in the power sector. Also, we are charging the EVs through our grid, so there are a lot of power quality issues that we need to take care. So as a power system engineer and power electronics engineer, we should have some minimum knowledge on this electric vehicle and the charging technologies associated with this. So with this, we could able to proceed the research in a better way, and also to solve the issues related with the power system. So that's the motivation for this lecture, I guess. So we will start the first session. In first session, let us see about the electric vehicle fundamentals. So this is the outline of my presentation. My outline of presentation goes like this. So first, I'll start with the introduction, where I'll be discussing the motivational facts behind the electric vehicle, and then I'll discuss about the difference between IC engine, that is the conventional vehicle, internal combustion engine vehicle, and the electric vehicle. And then I'll move on to further basics about the electric vehicle. where I'll be discussing about the powertrain components associated with the electric vehicle, and also I'll be illustrating a small example design for the electric vehicle, like how to design a motor and how to select the capacity of the battery for that particular vehicle. So after which I'll be discussing about the powertrain components. So powertrains are the components which are basically responsible for transmitting the power from the source to the wheels of the vehicle. So all the related components such as battery, converters, differentials, all this part will are the components of the powertrain. And then how these powertrains are controlled, what are the control strategies available in the literature, we'll just see an overview. And then finally the concluding remarks for this session. So let's proceed with introduction part. So there is a motivation for this electric vehicle market dominance. So there is a Paris Agreement which was held in 2015 in Paris, where it is an international treaty on climate change. So based on this Paris Agreement, the there is a treaty put forward that is holding means there is increase in the average global temperature. So we need to restrict this increase in the average global temperature well below 2 degree. So we need to limit this increase to 1.5 degree. So recognizing this would be reduce the risk and impact of climate change. So many countries have come forward for this treaty, and each of the countries have put forward their own SDGs, strategic plans to mitigate this climatic change. So for example, the UK based on this prioritization of decarbonization outlined in this Paris government, the UK government has committed to achieve net zero green energy emission by 2050. Also, our Indian government has put forward a lot of SDGs strategies to adopt green energy and the uh, electric vehicle technologies in Indian markets. So let us now see what are the primary factors associated with this. So first, with regard to that, the carbon dioxide emission from the fuel combustion in India, we will see. So there are many sectors which produce this carbon dioxide emission. So the major sector which is responsible for this carbon dioxide emission is the electricity and heat producers. So we are generating power mainly from the fossil fuel based energy sources, so which are primarily responsible for generating this carbon dioxide emission. So here our electricity and heat producers are the major producer of this carbon dioxide emission, and second comes the industry, where we have to use this while manufacturing we might be in a position to generate carbon dioxide and other greenhouse gases in the atmosphere. And third comes the transportation sector, where most conventionally now currently the conventional IC engine, that is internal combustion engines, vehicles are dominating the transportation sector. So which will produce a lot of harmful gases into the atmosphere, which is responsible for the CO2 emission as well. So the transportation forms the third basic sector in the carbon dioxide emission in the India. So there are other sectors as well, like residential sectors, commercial, agriculture, and financial consumption. So most of, I mean, these are not that significant when compared to the three major sectors. So since transportation lies in the third sector and generating the carbon dioxide emission, so we should try to give some importance to it, and we need to we need to adopt green technologies towards the transition. That's the reason why we are moving into electric vehicle uh, market. So second fact is that as you can see the plot which is given here in the right hand side, which shows the increase in the gasoline price from the year 1998 to 2022. So this is typically in Indian rupees. As you can see this plot, the graph is like increasing from 1998 to 2022. As you already know that most of our power generation plants are depends on the fossil fuel based energy sources. So also we are powering or fueling our vehicles based on this fossil fuel energy sources such as gasoline, diesel, and other things. So the fuel prices is also on in the increasing side. And the third factor, just to demonstrate that the what is the current installed capacity of power station in India. This is as on January 2023. So as you can see, around 50%, approximately around 50% of the installed capacity out of 411 gigawatt, around 50 percentage of installed capacity, which is 204 uh, gigawatt, is based on the coal, that is fossil fuel based energy sources. And now we are increasing this renewable. The second contributor in this chart is the renewable energy sources, RES, so which takes care about 121 gigawatt of electricity energy. So this trend is keep on increasing. When we look backwards, during 2014 or 2010, the coal based power station is dominating, so which was around 70% previously. So right now the coal based power stations are coming down, and the renewable energy sources, the power station based on renewable energy sources such as solar farms, wind farms, are increasing, right? So, and also there is a fact that the annual global electric vehicle sale is on increasing. It is estimated that in 2050, based on a literature, it is estimated that in 2050 the electric vehicle sale will hit 101 million, and the plug-in hybrid electric vehicle sale will hit around 50 millions, right? So the sales, or the dominance, the electric vehicle and plug-in electric vehicles are dominating the markets currently. There will be a huge demand in terms of power system for energizing these the vehicles, electric and plug-in electric vehicles. So as a power system engineer, we have this responsibility to mitigate this effectively. Yes. So based on these primary factors, so with regard to the transportation sector, how we can able to address this environmental concern? That is our primary objective. So one solution is that to use the battery electric vehicles. So in wider way, so wider use of battery electric vehicle will slightly reduce the environmental concerns, or the climate will eradicate the climatic change, and introducing hybrid electric vehicles to reduce carbon dioxide emissions. So all of a sudden we have investigated a lot of resources for generating the conventional internal combustion engine based vehicles, but we cannot suddenly move into the EV technology. So the technology will transfer through the hybrid electric vehicles, which means that it will be a combination of internal combustion engine plus electric vehicle here, right? So this is the way that we can move towards the electric vehicle. So first it will start with the hybridization, and then it will move to the electric vehicle dominance. So third is that we need to develop efficient energy management algorithms to use which is used in the hybrid electric vehicle. Especially in case of hybrid electric vehicle, we will be using internal combustion engine plus the battery electric vehicle, which is so how the power sharing is going to happen between this electric internal combustion engine and electric vehicles. So that is what we call as energy management algorithm. So the objective of this energy management algorithm is to achieve less fuel consumption, right? So how efficiently we can going to do that? So that is one possible way of addressing. And another possible way is that right now, as we have seen in the previous the chart, that 50% of our power generating sectors based on the coal based energy sources. So if you are charging our electric vehicle using our conventional energy sources, so it is again going to transform the pollution from the power generation sector to the transportation sector. So I'm sorry, so from the transportation sector to the power generation sector. So again the generating station will be emitting the the carbon dioxide emission and other greenhouse gases into the atmosphere. So the effective way of mitigating this is that using charging electric vehicles through renewable energy sources such as wind farms and solar farms. So that way we can address the concern, and using more energy efficient and less carbon intense energy sources. There are energy sources which will produce less carbon, so we have to effectively use that, and how we are effectively utilizing that, and also uh, how efficiently we are using that matters. So this I already have discussed. So these are the possible ways to mitigate this concern. And yeah, we'll now move into the history of automotive industry. So during the starting of or the earlier days of automotive industry, there were three vehicle technologies which were competing among each other for market dominance. One among that is the internal combustion engine based vehicles. So as you know, the internal combustion engine based vehicle, so it is powered by fossil fuel based or energy sources such as gasoline or diesel. So earlier, it has the problem of noise, difficulty in starting, and it has short driving range and lower maximum speed. These are the problems associated with the internal combustion engine vehicles at the early stage. So let's see the second vehicle industry which were dominating in the history, which is steam based vehicles. So here the water is heated and then it is converted into steam, and this steam power is used to run the or drive the vehicle. So there arise the issue of water preheating and amount of water required. Issue was there, so we need to carry a lot of water in the vehicle, and water preheating is also required. So because of these disadvantages, the steam based vehicle disappeared around 1920 in the market. And third comes the electric vehicle technology. So this electric vehicle technology was suffered from the short driving range. It was unable to climb steep hills and poor battery performance and lower maximum speed. So each and every industry, automotive industry has their disadvantages. So it is obvious that the industry which can able to solve these disadvantages faster will become the market dominance. So during the previous days, these internal combustion engine vehicles were able to solve the problem associated with the starting, and it was able to solve the shortest range problem. The range problem it has solved. So this industry was able to solve the problem faster, and I can say that they were the the industries that were leading the automotive industry till date. But due to the sustainable way of development, we are started to adopt the greener technologies. So that is the reason why we are now moving into the electric vehicle era, right? So right now, you can see the penetration of EV into the automotive sector. That is the reason. The reason being is that to eradicate the to mitigate the climatic change, right? Right. So now we are going to discuss about the basic difference between internal combustion engine and electric vehicle. So before that, we will see what is the as a vehicle, what is the minimum tractive effort required at the wheels of the vehicle. So this curve typically shows the tractive effort requirement for a vehicle, and the x-axis, in x-axis we have a vehicle speed, and in y-axis we have the tractive force required at the wheels. So during the initial acceleration phase, we need to require a constant, or I can say the maximum torque, and during the cruising phase, we have to require the less torque. So this is the ideal tractive effort requirement for a vehicle, right? Irrespective of either it is the electric vehicle or internal combustion engine vehicle. So this is the general typical tractive effort requirement for a vehicle. So the maximum torque is restricted by this friction, and the maximum speed is restricted by this road and acceleration vehicle losses. right? Yeah. So this can be further divided into two region. One is acceleration region, which is this, and the hyperbolic torque speed region, which is this. So this is hyperbolic torque region, and this is acceleration region. So this is the generalized typical requirement of tractive effort at the wheels. And now we will see what is the tractive effort required. What is the tractive effort for an internal combustion engine based vehicle? So these internal combustion engine based vehicles have the constant torque, and also it falls at the higher speed, right? So this is the tractive. If you could see the tractive torque, speed characteristics of internal combustion engine vehicle. So it will look like this. So initially, it has a constant torque, and then it will falls at the highest speed. So these characteristics, which we are seeing here, does not match the vehicle tractive effort requirements. So what is the vehicle tractive effort requirement? This is the vehicle tractive effort requirement. Initially, it has to have a constant torque during the acceleration phase, and the torque has to reduce hyperbolically once the vehicle picks up the speed. So this is the vehicle torque requirement. But we have the the torque characteristics of our internal combustion engine looks like this. Right. If you could match these IC engine torque characteristics with the ideal, traction curve, so it will just able to cover only a smaller region here. So So how we are going to cover the other part of the the tractive effort, actual tractive effort required by the vehicle? It is covered by using the gear arrangement, right? So we have gears in internal combustion engine vehicles only to cover the various regions of the actual tractive effort requirement of the vehicle. So as you can know, as we know that during the initial gear, that is low gear, we can see the torque will be higher, and once in the higher gear, the torque is less. So by having a different gear arrangement, we can achieve the actual tractive effort requirement for a vehicle. Right. Now let us see a torque speed characteristic of a electric motor. So for a fixed frequency of supply voltage, the torque speed characteristics is shown here. So this is the starting torque, and this is the full load operating point. So if you would vary the frequency of the input supply, for example, this is 5 hertz curve, and this is 30 hertz, and this is 45, and this is 60. So likewise, if you could vary the frequency of input supply to the motor, input supply frequency to the motor, we can able to cover the entire region of the tractive effort requirement for a vehicle. So by doing this, we can avoid the multiple gear requirement which is used in the conventional vehicles. So this multiple gear requirement become absolute in case of electric vehicles. So we are able to achieve this merely by changing the supply frequency. Merely by changing the supply frequency. So by frequency control, we can able to achieve the this characteristics. Means we can able to cover the complete characteristics of tractive effort requirement. Right. So this is just a definition for an electric vehicle. So any vehicle which is propelled by electric drivetrain, which can be taken power from the rechargeable battery or from portable refillable electrical energy sources. It may be from fuel cell, or it may be from solar panel, etc. So it is which is manufactured for use on public roads. So this is just a definition for electric vehicle. So we all know the advantages of electric vehicle. So as we know that it has high efficiency, and we can implement the regenerative braking in electric vehicle. So that is one of the advantages. It has much better acceleration, and also it can run on renewables. We can integrate renewable energy sources in electric vehicle, for example, by installing solar PV panels at the rooftop of electric vehicle. So we can able to integrate that, and it does not produce any exhaust gases. It has less moving parts, and it is light, compact, simple, and less in maintenance. So these are the several advantages associated with electric vehicle. Now let us see what is the range of an electric vehicle. So range is a parameter associated with the vehicle, which means that how many kilometers it can travel for a single charge. Okay, so the distance traveled by a vehicle for a single charge of the battery is what we call as range of an electric vehicle. Suppose, assume that we have a 40 kilowatt hour energy capacity of the battery. So battery capacity is 40 kilowatt hour, and we require 20 kilowatt to run the vehicle at 50 kilometer per speed. So we require 20 kilowatt to run at 50 kilometer per hour. So for in 1 hour, it will run 50 kilometer. For that, it requires 20 kilowatt power. So the battery now can release this 20 kilowatt power for 2 hours, because the battery capacity is 40 kilowatt hour. So it can run for 2 hours. So now the range is this 50 into 2, so which is 100 kilometer per charge. So this is how, we can calculate the range for an electric vehicle. Now let us see whether it is conventional. Is it economical when compared to the conventional vehicle? Economical in the sense, maintenance wise. Okay, so as you also already know that the electric vehicles are costlier when compared to the conventional vehicles. So that is mainly because of the cost of the batteries. So as the technology improves, it is expected that the cost of the batteries also will come down. So let us now compare how it is economical with regard to the maintenance. So let us take an average vehicle, uh, the mileage given by average internal combustion. This is internal combustion engine based vehicle, right? So the average mileage for internal combustion engine vehicle is 50 kilometer per liter. For 1 liter of let us assume that based on the current price, let us take 1 liter of gasoline is 100 rupees, right? So for traveling 1 kilometer, it requires we need to invest 6.6 rupees. So we will take the same 40 kilowatt hour battery with 120 kilometer range. So 1 kilowatt hour electrical energy cost, let us assume that it is 8 rupees. So for traveling 120 kilometer, we just require 320 rupees. So if you calculate per kilometer charge, it is 2.6 kilometer, 2.6 rupees per kilometer. So we can compare. So it is the maintenance cost or the running cost of electric vehicle is much cheaper comparative to the conventional based electric vehicle. Okay, just a moment, let me just switch off the camera for a bandwidth issue. Okay, now before we will move into an EV design, where I have told in the introduction that I'll be demonstrating a simple EV design. So like how to design the motor rating. Yes, hello, am I audible?
Yes,
Yes,
sir.
yes, yeah. So we will see how to design how to decide on the capacity of an electric motor, and how to design the charge requirement for the charge requirement for the by the battery, right? So let us take an electric vehicle and analyze that. How much, what is the motor capacity required, and what is the battery capacity required for a particular velocity profile, right? So if you take a vehicle, as you know that there are a lot of resistive forces which are acting on the vehicles in order to restrict the forward movement. One among them is this aerodynamic drag resistance, so which is expressed by this. And the other one is due to the tire friction between the tire and the road surface, which is represented by this. Okay, mg CRR cos theta, and the other resistive force is due to the gradient, which is the gradient of the road, so which is represented by this mg sin theta. So these three are the resistive forces which are restricting the motion of the vehicles to move forward. So vehicle has to move in this direction, but there are three resistive forces which are acting on the vehicle, which resist the motion of the vehicle in the forward direction. So this is the vehicle so this is the vehicle direction, and this is the, let us say, the wind direction is just opposite to that vehicle. So in that case, you can see from this from the formula that it will be greatly affected by the wind velocity. So vw is the wind velocity and v is the vehicle velocity. So there are three basic resistive forces that we can consider for this analysis. So the acceleration of the vehicle is determined by all the forces acting on the vehicle. So based on the Newton's second law, we can formulate this. So m into the m alpha acceleration is equal to the attractive force Ft minus the resistive forces. Fr is the resistive forces and Ft is the tractive force. So here m denotes the overall mass of the vehicle and alpha is the vehicle acceleration, right? And Ft is the total tractive force to the vehicle. So this is the total tractive force. So the total tractive force, in order for the vehicle to move forward, has to overcome this resistive forces. This, what are the resistive forces? There are three resistive forces. One is aerodynamic resistance due to wind, and resistance due to tire friction, resistance due to tire friction, and resistance due to slope. So these are the three resistive forces that we have considered for this analysis. So the tractive effort produced by the vehicle has to overcome this resistive force in order for the vehicle to move forward. So Ft is the total tractive force and Fr is the total resistive force. So if you calculate, so this is the total resistive forces, which is the summation of these three, resistive forces which we have discussed previously. So this is due to the, the friction between the tire and the road surface, and this force is due to the aerodynamic, due to the wind, and this is due to the slope or the gradient. So yes, these are the three forces which I was talking about. So here, when we take this rolling, the friction resistance, here G is the acceleration due to gravity, and M is the vehicle mass, and CRR, which is the important factor here in this particular, force, is that CRR, which is the coefficient of rolling resistance between the tire and the road surface, right? So and here is the aerodynamic resistance, which is due to the wind, and rho here is the density of the ambient air, and capital A here is the vehicle frontal area, and CD here is the aerodynamic drag coefficient, and V is the capital V is the vehicle velocity, and V suffix W is the wind velocity, right? So alpha and theta, which is another factor, which is the slope angle or the gradient angle here. As you can see here, this is a slope or gradient angle. So these are the factors associated with the resistive forces. Okay. So the total tractive force, okay. So from this equation, if you want to compute what is the total tractive force, then we have to take this, resistive forces on the other side. So this is the final equation. So these are all the resistive forces. So if in order for the vehicle to move forward, it has to overcome these resistive forces. Okay. So this is the total force. If you want to calculate the total power, we need to multiply this force with the velocity. So if you multiply this whole right hand side with the velocity, so the equation is changed in this way. Now let us do the calculation, power calculation, which means that how much power is required for the vehicle in order to move forward. So for that, we have to consider some, example. So let us take the mass of the vehicle is 1000 kilogram, and we are aiming the velocity of the vehicle at 100 kilometer per hour speed. Okay, so this is the velocity, desired velocity we have taken, and the mass of the vehicle is given. So we are just going to substitute. We already derived what is the power required for the vehicle in order to drive at a particular speed. So this is the formula. So other are the constants. Okay, so we are going to assume that acceleration. So initially we will be computing what is the power required by the vehicle in order to overcome the resistive forces alone. Okay, so as we have discussed previously, there are three resistive forces. So in order to overcome this resistive force alone, what is the power required, we will be seeing. And for that we have assumed the acceleration of the vehicle, as 0. Okay, and rho, and this is the frontal area, and rolling resistance, wind velocity we are assuming 0, and gradient also we are assuming 0, and this is the drag coefficient, which is assumed to be 0.5. So with this, if you could substitute these values to the above equation, and this is just for the simplification, that converting simplification, which shows the conversion of kmph, kilometer per hour, to meter per second. So 100 kilometer per hour is converted to meter per second. So if you convert, it is 28 meter per second, and this is just conversion of 50 kilometer to 50 kmph to meter per second for 150. So we will be using directly this in the next forthcoming calculations. So just for that, so if you could substitute the value of these parameters in the above equation, we'll be getting, so mass is 1000, so acceleration is 0, which is denoted here, and again mass is 1000, which is denoted here, and g, which is acceleration due to gravity, which is 9.81. CRR is the rolling resistance. Here it is assumed as 0.02. It is substituted here, and cos theta. So initially we assumed theta is 0 degree. So cos 0 is 1. So into 1, right? And then 1 by 2, which is 0.5. And A, rho is 1.2, which is mentioned here. So if you could, we have to just simply substitute all the parameter values to this equation. So if you could substitute, and V, the velocity we have considered as 100 kilometer per hour. If you convert that into meter per second, it is 28. So I'm just substituting this 28 here. So if I could substitute, then it will yield 18.94 kilowatt hour. So this is the power which is required by the vehicle in order to overcome the three resistive forces, right? So right now the vehicle is at standstill. So just to begin the vehicle, we need to overcome these resistive forces. To start the vehicle, to move forward, we need to overcome these resistive forces. For that, we need to require this much of power. Now let us see what is the power which is required for the vehicle for accelerating the vehicle from 0 to 50 kilometer per hour in 10 seconds, right? So for this, we require an acceleration of 1.38 meter per second square. So I'm just substituting this power equation. So power is equal to force into velocity. Power is equal to force into velocity. So force is mass into acceleration. So this is mass, and this is acceleration, and this is velocity. So if I could substitute, I'm getting 38.64 kilowatt hour. So this is the power which is required for the vehicle to move in this velocity in this particular time. So if you could sum up these two, right, 38.64 plus 18.94, we will get what is the actual power requirement for the vehicle. So also, so this is the actual power requirement, 57.50 54 58 kilowatt is the actual power requirement for a vehicle. So how can we choose a motor? We have to choose a motor in such a way that it is capable of operating with this power, 58 kilowatt. So now let us see how to choose the battery. So assume that the same condition, and then we are assuming the time taken to discharge the battery from the maximum level is 1.5 hours. So also we have to take care of the additional power for the battery. So we will be considering 50% more power. So the battery capacity would be this power, the power of the motor, which is 58 into 1.5 times, means this it has to discharge. In order for the discharge of the battery from the maximum level, we are assuming 1.4. So this 1.5 will be coming here, and for the additional power requirement, this is the factor 1.5. So the finally it is computed to be 130.5 kilowatt hour. So this is the requirement battery power requirement for satisfying this profile. So let us see the total distance covered by the vehicle. So we are running at 100 kilometer per hour. So we assumed that the battery is discharging the power in 1.5 hours. So if you run at 100 kilometer per hour, so this will be multiplied by 1.5. So we'll be getting 150 kilometers. So we'll be able to cover a total distance of 150 kilometers using the motor power of 58 kilowatt and the battery power of 130.5 kilowatt. So roughly we can have an idea of what is the actual power required by the motor and the battery using these formulas. So now let us see how the plot of this power calculation will look like. For that, I have taken a velocity profile. So 0 to 20 seconds, it is in acceleration phase. Okay, this is the acceleration phase, after which we will be maintaining the speed constant. It is cruising phase, I can say. So 0 to 20 is the acceleration phase, and 20 to 40 will be the cruising phase, that is constant speed phase. So this is the velocity profile. In other words, these kind of velocity profiles with vehicle terminology is called as driving cycle. Driving cycle, you can see there are different driving cycles available for the vehicle for the testing purpose especially. So for example, there is Indian driving cycle. So right now they are testing in NEDC, new European driving cycle. This is the standard of driving cycle which is followed for the testing of electric vehicle, based on which they will be giving what is the range of the vehicle. So which is nothing but driving cycle is the one which is the velocity profile of the vehicle, which means that what will be the velocity. So x-axis will be the time, and y-axis will be the velocity. So with regard to time, what will be the velocity of the vehicle? So it will have some certain pattern. Each driving cycle will have certain pattern, and mostly our the driving conditions will also vary based on Indian roads and based on the foreign roads, especially in Europe. So the Europe countries and other foreign countries, they have their own driving cycles like this in order for testing the vehicles at their environment. And we do have our own driving cycle, but recently we are following NEDC, new European driving cycle, as criteria to compute the range of a vehicle, right? So now we'll move on to this. So this is the velocity profile that we are considering. So for this velocity profile, what will be the power required for the acceleration? If you can see this cyan color, this is the power required for the acceleration, and this is the total tractive power required, so which is more or less 58, okay, 58 kilowatt. So which is matching our previous calculations, right? So, and this blue line indicates the power required to overcome the rolling resistance, and this green represent the power required to overcome the drag, right? And this color represent the power required for the acceleration. So if you could sum up these three powers, we'll be getting this total tractive power. So the total tractive power requirement will be around 58 kilowatt, right? So this is how a power requirement curve looks like. Okay, so now we'll move on to the drive train. So drive train is a mechanism to transmit the power from the source to the vehicle wheels, I can say, or otherwise it can transmit the drive from the engine or the motor of a vehicle to its axle. So it comes. So we will generally say the powertrain components, which means that the what are the components which is coming in line in between to accelerate this process, or to which can generate the power and deliver it to the road. So what are they are the basically the components which are responsible for generating the power and as well as delivering it to the road surface. For example, the powertrain components may be engine in case of internal combustion engine, or in case of electric vehicle, it is electric motor. It is battery, transmission, drive shaft, suspension, wheels. So from the source to the wheels, what are the components associated with that? So all these are called as powertrain components. So based on the powertrain components, there are different vehicle architectures available in the literature. One is we already know that these are the conventional vehicles, which is based on the internal combustion engine, right? So internal combustion engine vehicle. So internal combustion engine vehicle will have a architecture like this. Internal combustion engine. It is connected to gearbox using the clutch arrangement, and then the power goes to the differential, and from differential the torque is splitted among the two wheels, right? Like in this way. So there are advantages, means faster refueling. That is one of the major advantages when compared to the electric vehicle, which is once we are the fuel is down, we can go to the refilling station and we can just fill it in 1 minute, less than 1 minute, I can say. So fast refueling is one of the advantages of internal combustion engine, and we can able to go for a long range and low cost per unit. There are other disadvantages as well. So like the main one is the exhaust gas and the noise it is producing, and it is less efficient. So these are the primary disadvantages of internal combustion engine. In order to overcome these advantages only, we are moving into the electric vehicle. So this is the typical architecture of an electric vehicle. So as you all know, the electric vehicle consists of electric machine, which is powered by the batteries. So batteries are basically powered by the DC sources. So we need to have, suppose our machine is a AC machine, or the permanent magnet synchronous machine, or BLDC machine, whatever. So based on the power requirement of the machine, we need to convert the power from the battery. So for that, we need to have a power electronic interfaces, right? Also, we can see there is a less gear arrangement when compared to the conventional vehicle. This is because we can able to cover the complete tractive effort using the control possible. For example, the frequency control, as I illustrated in the previous slides, right? So further, it has these advantages which we have already seen, and disadvantages is that shorter range, that is further limited with the battery capacity, and higher battery cost. This is really a disadvantage for electric vehicle, because as the technology improves, this is further it is proposed that it will come down the cost of the battery. So low energy density and better. Okay, so there is another category of vehicle which is called as series hybrid electric vehicles. So if you call a hybrid vehicles, which means that it is using internal combustion engine as well as electrical machine, right? So in case of series hybrid electric vehicle, we have this internal combustion engine as well as the electrical machine. uh, this internal combustion engine in this case is used only to charge the battery of the electrical machine. Okay, so this is the battery which is powering this electrical machine. So this internal combustion engine machine is coupled with a DC generator which will generate the power. So this generated power is then utilized to charge the battery. So we have a power electronic interfaces for that. So these specific architecture, that is series hybrid vehicle architecture, also called as range extenders, because they are used to charge the batteries. If you charge the batteries, we can able to travel additional kilometers. Okay, so they are specifically called as range extenders in the literatures. Coming to parallel hybrid electric vehicle. So in parallel hybrid electric vehicle, these internal combustion engine will participate, or will help the electrical machine to make the vehicle move forward. Means it helps in the tractive effort requirement, right? So that is the reason why it is called as parallel hybrid vehicles. Okay, so the torque which is produced by the internal combustion engine machine as well as the torque produced by the electrical machine together help the machine or the vehicle to move forward, right? So that is the reason why it is called as parallel hybrid electric vehicles. So this is the typical example. This is a typical efficiency map of an electrical machine To be specific, it is for the this is electrical machine. Here we have an torque in the y-axis and speed in the x-axis, and this is called as map because we are mapping the efficiency also in the torque speed characteristics. So as you can see here, we have a higher efficiency at this region, and uh, uh, lower efficiency as the speed increases. So the lower efficiency here is computed to be some 84%. So if for a typical permanent magnet synchronous motor, if you could take, the minimum efficiency would be 70 to 75 percentage, and maximum would be 95 to 97 percentage. And on an average, we can achieve 85 to 90% efficiency. So this is the efficiency the fuel consumption map, I can say, for the internal combustion engine. So this is internal combustion engine, and this is electric motor map, right? So if you can see the internal combustion engine efficiency, it is very less actually. So compared to the electrical engine vehicle, so this may range between 10 to 45%, and the average efficiency would be 25 to 30%. So control strategies used in hybrid electric vehicles. So hybrid electric vehicles, we have just seen that it is a combination of internal combustion engine vehicle plus the battery electric vehicle. So internal combustion engine plus battery electric vehicle. So how we are able to manage the power among these two is what we call as energy management of the hybrid electric vehicles. So based on this, it is further divided into rule based and optimization based. So there are further categories. These are the areas where optimization researchers will work with regard to this energy management of hybrid electric vehicles. For example, in optimization, we have this global optimization. For that, we have this linear programming, dynamic programming, and other stochastic controls. When you take the real-time optimization, there comes this EC minimization, neural networks, particle swarm optimization, and other techniques. So these are the various optimization coming under the hierarchy of rule based and optimization based control strategies, right? Coming to the conclusions, so electric vehicle will be a best alternative for internal combustion engine vehicles, which has zero tailpipe emission, which is of course 0% emission, and EV design with regard to electric motor and battery capacity were analyzed in this presentation. And hybrid electric vehicles helps in reducing the CO2 emission into the atmosphere when compared to the conventional vehicles, of course. And powertrain control algorithms are employed to effectively manage the power and utilize the power from source to the load. So this is with this conclusion, we will move forward with the second section. Sir, can we proceed with the second session?
Yeah, you can proceed.
Yes, yes. Thank you for the confirmation. Okay. So in this section, we'll be seeing about the electric vehicle charging technologies. So the outline of my presentation goes like this: introduction, uh, where I'll be discussing about the battery charging requirement for an electric vehicle, and then we will be studying about the battery technologies of electric vehicle, and then the EV charging basics. For example, how the charging profile of an electric vehicle or the battery electric vehicle battery will look like. What are the different phases associated with that? We'll be seeing, and then regenerative braking, a typical example case, a typical case we will take, and we will analyze how the regenerative braking is implemented in electric vehicle. So, and then we will be seeing the future technologies for the electric vehicle, followed by the conclusion. So this is how I'm going to cover this presentation. Let us move into the introduction part. So as we all know that the electric vehicles are powered by the batteries, which are the DC source, right? DC source. So this charging of electric vehicle means we need to supply the DC current. We need to supply the DC current to the battery. So then only the battery can charge. Suppose as the electric distribution supplies this AC power, so in our household we are receiving AC power, so we cannot directly connect this AC power to the battery. We require a power electronic interfaces to convert this AC power to the DC power, and then based on the battery requirement we'll be giving it to the battery for the charging, right? If the distribution system is of AC. So this is done. So further charging can be AC charging as well as the DC charging. In case of AC charging, the AC power is delivered to the onboard charger. In case of AC charging, there is an onboard charger available in the vehicle which converts the AC into DC and stabilize the power based on the requirement of the battery, right? In case of DC charging, the all the conversion will takes place outside the vehicle environment in the charging station exactly. So DC which converts the power externally and supplies the DC power directly to the battery. So in this case, in case of DC charging, we don't have to have the the power electronic interfaces inside or on board in the vehicle. So all the conversion from AC to DC will takes place outside the vehicle environment, that is in the charging station, and directly the DC power is sent it to the battery. Right. So this is a table which typically shows the battery capacity and the battery voltage requirement for a different vehicle segment. So there are basically different vehicle segments available with regard to electric vehicle. One is the two-wheeler vehicle. Okay. So basically, as you know that there are different two-wheelers available in the current markets, Indian markets, popularly. So these two-wheelers are generally powered by the battery with this capacity, that is 1.2 to 3.3 kilowatt hour capacity. Usually we'll have this capacity, and if you take the voltage, if you could see the voltage of this battery, it will be like 48 from 48 to 72 volt. So in four-wheeler category, we have this battery capacity of 3.6 to 8 kilowatt hour. So with this, the battery voltage again, it is 48 to 60 volt. And coming to the first generation electric vehicle, we have this capacity of 21 kilowatt hour. So generally, if you take a very basic electric vehicle, that is four-wheeler electric vehicle, I should say, the battery capacity will be like from 21 kilowatt hour, and the voltage requirement for the battery is 72 volt, right? So in second generation electric vehicle, that is the vehicle which is suitable for a long driving range, the battery capacity somewhere lies between 30 to 80 kilowatt hour, and the battery voltage will be in this range, 350 to 500 volt. So this table just gives us an idea about what is the battery capacity that are used in different vehicle segments, such as two-wheeler, three-wheelers, and the four-wheeler based electric vehicles, along with the battery requirement, so battery voltage requirement, right? So in order to understand this charging technology, and we need to have some basic understanding about the battery. There are various terms that are used in battery performance. So first comes the cell. So we will call as a cell. It is a single cell is the complete battery with two current leads and separate components holding electrode separator and electrode. So it is a complete battery is what we call as cell. Further, the cells are uh, you know uh, you know used in a different combination, which are called modules. So which is basically composed of a few cells, either by connecting physically using physical attachment, or by welding in between them. So based on the voltage requirement, these cells are connected together, right, in series and parallel based on the voltage. We have just seen in the previous table, right? For a two-wheeler segment, we need to have some 48 to 70, 72 volt. So if you could connect the voltages in these cells in series, we can increase the voltage range. So module is a thing which is composed of fuel cells, which is connected together to satisfy the the voltage requirement. And pack is, it is composed of modules and placed in a single compartment for thermal management. So an EV can have more than one pack of battery situated in different locations in the car. For example, if you take a four-wheel electric vehicle, we have this main battery which is going to power the electric vehicle, and also we have an auxiliary batteries which is used to power the our headlights, fan, and other small accessories, right? So yeah, the other term that we are going to see is ampere hour. So this is more familiar for us. Ampere hour, it is the capacity of the battery can be specified in ampere hour. It is a total charge that can be discharged from a fully charged battery under specified conditions. So this is what we call as ampere hour. Right? Coming to specific energy, so this is also this is called as gravimetric energy density. So it is used to define how much energy a battery can store per unit mass. Also, the specific power can tell that what is the peak power per unit mass. So this is what we call as specific power. Both are based on the gravimetric uh, term. So the energy is associated with gravimetric energy density, and the power is associated with gravimetric power density. Coming to energy density, so previously we have seen specific energy and specific power, and this is different energy density. So these terms I will be using for specific then and there in the battery charging and other EV technology, EV terminologies. So energy density is also referred to as volumetric energy density. So it is the normal battery energy per unit volume. Power density is the peak power per unit volume. So there is one more term called internal resistance. So as you all know that the battery has the internal resistance, and this internal resistance will vary. Uh, Based it will be different for charging as well as discharging condition, and it may vary based on the operating conditions as well. So there is a term called peak power. According to this ABC, which is US Advanced Battery Consortium. So based on this, the peak power is given by this, where VOC is the open circuit voltage and R is the internal resistance of this battery. So from this, we can calculate the peak power of the battery. Another important terminology which we'll be using frequently in the literature is that SOC, which is state of charge. So this simply tells us what is the remaining capacity of the battery with respect to the rated capacity. So this is what we call as state of charge. Coming to depth of charge, which is called as DOD. So it is used to indicate the percentage of the battery capacity that has been discharged. Simply we can calculate this by with SOC. 1 minus SOC will give you the depth of discharge. Another important factor is the state of health of the battery. As we all know that when we are started using the batteries for a long time, the SOC, the state of health of the battery will come down. Means the charge capacity will get reduced. So for the aged battery, I mean for the battery is used for number of charging and discharge cycle, the energy density will be less. So aged energy density capacity upon the rated energy capacity, which means for a healthier battery or the new battery, which will give the SOH. So the battery health is determined based on this. Coming to cycle life or life cycle of a battery, so which means that we are doing charging, discharging, charging, discharging again and again. So it is just the number which says that how many times we have charged and discharged the battery. And another important factor is the C rate. We have generally heard the C rate of the battery, which means that charging rate. This is also used to represent charge as well as discharge rate. This is just equal to the capacity of the battery in 1 hour. Okay. For example, we will consider this a 5 ampere hour battery. If you take a 5 ampere hour battery, 1C means 1C is equal to charge or discharge. It is applicable for charging as well as discharging condition. So for charge or discharge, the battery, the 1C of the battery is 5 ampere. Okay. For example, 0.1C means 10% of this 5 ampere. So correspondingly, 0.5 C is equivalent to 10% of 5 ampere, which is 0.5 ampere. If you say 2C, then 200% of this ampere hour capacity, uh, which is in this case 10 ampere, right? Suppose if we have a 5 ampere battery and we are going to charge this 5 ampere battery with 5C rate. 5C rate means so we need to just multiply this C charge rating with the actual capacity of the battery. So we can charge this battery with 25 ampere of current. So that is the meaning. So another important factor is that BMS, battery management system. So this is very important to preserve the health of the battery or the safety of the battery concern. So during it actually monitors and controls how much charge the battery or how much current the battery can be used, how much charge can be used for the battery to charge, what is the maximum discharge it contains. So it is basically a software along with sensors and other parts, so which is basically used to protect the safety of the battery. So if we have a good BMS system, we can say that the health of the battery and safety of the battery is ensured. And as we all know that the battery will get heated up during charging and discharging process. So in order to preserve that heating, we have this battery management system in order to take care of the temperature. We have this battery management system. So further it is done using thermal management system, which takes care about the temperature. So we are doing the forced air thermal management system for nickel metal hydride batteries. And also the liquid based thermal cooling system is also followed for the lithium ion batteries used in EVs, electric vehicles. Okay, so these are the different terminologies that we should know in order to understand these battery dynamics. Now, let us see what are the current battery technologies used in the EVs. One is one popular technologies that was used previously was lead acid batteries. So lead acid batteries actually it is bulky actually. So when compared to lithium ion batteries, it has less energy density. So lithium lead acid batteries and nickel metal hydride batteries. Nowadays, lead acid batteries are being replaced by lithium ion batteries. So these are the three battery technologies that are used in electric vehicles. So in the emerging field of energy storage technologies, we are using the fuel cells, which is having a high energy density, and also ultra capacitors. So ultra capacitors are basically used for EVs applications to observe the spikes coming because during charging or during regenerative braking, we may have to send high current into the battery, which may have some spikes. So the ultra capacitors will take care of this spikes. So and also it will helps the battery it helps ensure the battery safety. Okay, so fuel cells are basically the energy sources which are used to generate the electricity by means of chemical reaction of two material. One is fuel and accident. So we have a two element anode and cathode. So to the anode we will be supplying the hydrogen, and to the cathode we will be supplying the air. So based on this there will be separation of protons and electrons in the anode region, and these electrons is conveyed to the external circuit. So this is how the electricity is generated in the fuel cells. So this is a one technology for the energy storage. So it has high energy conversion efficiency, and it is low fuel cost. Similar to the fueling of gasoline and petrol, the refueling takes place much lesser time in compared to battery charging, and it can have a long driving range. The disadvantages associated with this fuel cells are the high initial cost. For example, it is 5 times costlier as that of the IC engine with the same capacity, and low energy density and higher weight are another disadvantages for this. The efficiency reduces with increase in power rating. These are the disadvantages associated with fuel cell technologies. Coming to ultra capacitors, this has higher capacity than electrolytic capacitors. It has high power density as well. Also it can handle large currents. Okay, so this is faster. It can the faster charging and discharging takes place in ultra capacitors when compared to batteries. So that is why I've said this is used to observe the interruptions and spikes which are occurring in EV during charging or during the regenerative braking operations. Right. Now we will see the battery profile actually. So a typical battery profile will look like this actually. So this is very important as far as the EV charging is concerned. So EVs are powered by batteries. So we'll be charging these batteries using chargers. So how a battery can be charged will be dictated by this battery profile. So any battery manufacturer data sheet, if you could take for a specific model of a battery, they will be providing with you with the sheet that what is the what is the charging current for that battery, and what is the maximum voltage for that battery. So all these things will be clearly given in the data sheet or the specification manual of that particular battery. So we need to follow that specification data sheets for the battery charging process. So it will start like this. So initially we need to charge the battery with this constant current. So this constant current will be dictated in the will be given in the manual or the data sheet of the battery. So for example, a 48-volt battery system can have a charging current of maybe 47 or 45 ampere of current. So we need to charge the battery with this 47 ampere of current, right? Okay, so initially the charging phase will be started using the constant current mode. So during this constant current mode, if you could see, the SOC of the battery will be increasing linearly, right? At the same time, you can see this curve is the battery voltage curve. This curve is the battery voltage curve, and this curve is the current curve. And y-axis we have the x-axis we have the time, and y-axis we have this current and voltage parameters. So initially a constant current mode is activated, and a constant magnitude of current, let us say 47 ampere of current, is passed by the is delivered by the charger to the battery. So during this process, as you can see, the voltage of the battery will gradually increase, and it will reach a maximum point. So this is what we call as the predefined threshold of or we can say the maximum rated level of the battery. So which is typically corresponds to 70 percentage of the battery capacity here. So this point, so it is a predefined threshold maximum rated level of the battery, which typically corresponds to 70 percentage of the battery capacity. So if the battery charging is continue to reach 100 percentage of the rated capacity using this constant current phase, the battery voltage will increase beyond its maximum rated value, which then damages the battery and cause excessive heating. So we are adopting or changing the charging phase to constant voltage phase. So at this point, the constant voltage phase is activated, which means that we are maintaining the battery voltage constant from this phase onwards. So if you are maintaining this battery voltage constant, then the current which is taken by the battery will be automatically decreased in an exponential way, and it will reach a minimum value. This minimum value is what we call as the 10 percentage of the full charging current. So it is 0.1 into full charging current. Let us say maybe if this the full charging current is 47 ampere, so maybe it will reach to 4.7 ampere here. So once it reaches to 4.7 ampere, it is assumed that the battery is fully charged. So this is just a typical charge profile that we need to follow for charging the batteries. Right. Now we will see what are the different standards that are available for electric vehicle charging. So we have different standards like SAE J2293, which will tell us about the energy transfer system for the electric vehicles. And also we have this SAE J1772. So this is used for electric vehicle conductive charge, and SAE means Society of Automotive Engineers. So they are defining their own standards that we need to follow for during the for the electric vehicle charging system. So this SAEJ 1773 will tell us about the inductive charging. So there are basically two charging. One is conductive charging, and another one is inductive charging. Inductive charging is what we call as this wireless charging, right? So in India, based on this BIS Indian standard, we are following this IS 17017 standard for electric vehicle charging. Okay, so we are following these standards, which will give a complete details about how to test the charger. Okay, for example, if you are designing a 3.3 kilowatt charger, then what are the tests this charger has to satisfy? So we need to follow this test. Even they will be giving what is the voltage level, and what is the current level that you have to follow during the testing phase. So we have to our the whatever the charger we develop has to come through this test and pass this test. So once we pass this test, they will give the approval or the certificate that yes, this your charger has been passed with this voltage surge test, or the thermal test, or overcurrent test, whatever. So there even the EMI test, which is very important in case of chargers, electromagnetic interference. So the charger that we have to will be designing should be compatible of not interfacing with other electrical appliances in the nearby periphery. So there are several standards and testing procedures which will be given in the standards that we have to adopt, and we have to make use of that for clearing the test. Right. So this is a typical electric vehicle energy transfer system based on the applicable standards. So this is a grid where we'll be taking the power to our utility. So as you know that as since we are taking power from the grid, we need to make sure the power quality issue. So the power which we are drawing from the grid should have the near unity power factor. And once we are into the grid, then through this branch circuit, we are connecting to we are making a provision to EVSE, right? So from here it is then the power is then transferred to the electric vehicle. It may be through DC charging or AC charging. If it is an AC charging, we have a converter inside, and then for the power electronic converter inside to stabilize the power requirement of the battery. And if it is a DC charging, we will have this power electronic converter external outside the charging, outside the vehicle environment, and the direct DC power is given to the battery for the charging. So in addition to that, we have this power electronics, converters or inverters, along with the motor controllers. So there will be a motor controllers drive, which is used to drive the electric motor at the required frequency and the voltage, whatever, to control the speed and other operation, right? So this is the typical energy transfer system that is applicable based on the standards. As you can see, there are various standards. For example, in order to maintain the power quality, we need to follow this IEEE standards. And for the vehicle charging system, we need to follow IEC and SAE, International Electrotechnical Commission, and Society of Automotive Engineers. So we have just seen the different standards available for the charging system. So we need to adopt these chargers at different levels. For example, for example, taking power from the grid to charging the batteries of an electric vehicle, right? So based on this standard, that is SAE J 1772 standards, they are categorizing this EV charging based on the power level. So for example, the level 1 charger will have this power charging power, which is 1.5 to 3 kilowatt, and level 2 charger will have this power from 10 to 20 kilowatt, and level 3 we have this 40 kilowatt and above. This is categorized based on this standard SAE J1772 standard. So level 1 chargers are typically suited for our household appliances. So uh, I mean, household power supply, using household power supply, the maximum that we can design the charger is like 3.3 kilowatt hour. So level 1 charger is basically we are charging the batteries of the electric vehicle using the power available at our homes. Coming to level 2 charger is basically a common charging station where you can charge the electric vehicle. And coming to level 3, it is about the fast charging actually. So fast charging means DC charging. So we will see in detail what is the constraint that restricting us in the onboard charger, right? So in case of level 3, we do not have any restriction in terms of component size and other requirement. So we can have a bulk component system which can give a high DC power which is used to charge the battery, and hence the battery can take a high DC power and it can charge at a faster time, right? So usually what happens is that when we see any electric vehicle, they will be mentioning about this charging parameter. So which is basically from this point to this point, that is during the constant current phase. So maybe at the end of the constant current phase, the SOC will be something around 80 percentage. So they will be mentioning like you can charge the for charging the battery from 0 to 80 percentage of the SOC, it will require only 1 hour, like that. So why this time is short? It is because of the constant current, which is a constant high magnitude of constant current that is being supplied from during the initial phase. So they'll be dictating this only. I mean, in the constant current changing phase, how much the bat I mean how much the SOC can be charged. Like for example, to charge from 0 to 80 percentage of the SOC, we require only this much amount. So this is one of the parameter that you can find in any of the EV vehicle specification. So basically, it will take a quick time to charge to 0 to 80% because of the constant current charging. So after 80%, definitely it will take a lesser time, long time, because you can see here the charging current is getting reduced. Okay, so it will take some higher time probably. Right. So these are the various power levels which are classified based on this standard. And coming to charging methods, as we already seen that there are two different charging methods. One is conductive charging and the other one is inductive charging. Coming to conductive charging, we have AC charging, that is we have AC power, and we are plugging the socket of this charging socket of a car, of an electric vehicle, to the AC charger, and then this AC power is then converted to DC, that is suitable for charging the battery using the onboard charger. So in onboard charger, we have the power electronic interfaces to convert this AC into DC, which is suitable to charge the battery. See, based on the power rating, see, based on the size of the component, the power rating of the component will be decided. So there is a restriction that the vehicle has to have this much of weight and this much of space. Within that space, this onboard charger has to occupy. So there are, because of this limitation, it is usually there is a limitation in the onboard charger requirement. And then the output of the onboard charger will be the stable the stable power which is required to charge the battery. Coming to DC charging, we have this conversion taking place in the charger board itself. So that we call as off-board charger, because the charger is present outside the vehicle environment. So there is no space constraint and limitation on the power rating, because the charger is present outside the vehicle environment. So here you can see there is no charger, onboard charger present in the vehicle in case of DC charging. And the advantage is that we can deliver a high magnitude of current to the battery based on the requirement without any limitations. So that is the advantage of DC charging, and because of this advantages, we can able to charge the battery at a faster rate, right? So charging time, it reduces gradually. Okay, coming to inductive charging, we have this this is also called as wireless charging basically. So it is like will be having a two coils. It is based on the principle of mutual induction, that is similar to how our transformer works basically. So our transformer works on the principle of mutual induction. It has two coils, primary and secondary. So when we energize the primary, power is transferred to the secondary by the principle of mutual induction. So which is more or less similar to this principle which we are using for wireless charger. So there will be of primary coil, and there will be a secondary coil. Primary coil will be associated with the charger, and the secondary coil will be usually in the vehicle level. So here in this case, this is the primary coil, and this is the secondary coil which is located in the vehicle. So because of the mutual induction, the power transfer takes place from the primary to the secondary coil, and that is how the charging takes place. Since there is no direct connection between primary and secondary, this is called as wireless charging method. So in wireless charging method, we have two categories. One is static and other one is dynamic. In case of static, there will be a primary coil located at one place, and the secondary coil is located in the car. So we'll be parking the car exactly over the primary coil. I mean, to align the primary coil and secondary coil. So this is like static charge. This is called a static charging, because we will be charging the vehicle at only one particular place. So there will be a parking slot available. We need to go and park that car at that specific place, and the car will get charged. In case of dynamic charging, the charging takes place during the movement of the vehicle. For example, the primary coils of the charger are present below the road surface, okay, or buried below the road surface, and the vehicle will be in the movement. So during the vehicle movement, the charging takes place. So I mean, this kind of technology is what we call as dynamic charging. And another terminology, this is actually not charging, but it's a technique that is used in the EV industry, which is called as battery swapping. So as we know that the charging of the battery, it takes more time, right? So in order to overcome this, the policymakers have put forward this battery swapping solution. There will be battery swapping stations available similar to the battery charging stations, where we can go. Suppose if our battery is drained, that is the SOCF battery have come down to, let us say, some 80%, then we can approach a swapping station available, and then we can exchange our the less SOC battery with a healthy battery, and then we are off to go. means we are ready to go. So with this battery swapping process gives an advantage that it greatly reduces the the refueling process. So this technology we can use in order to avoid the battery charging time. Okay. In case of conductive charging, we have merits as well as and demerits as well. Let us see the merits. So we can charge. So this is a conductive charging, to be specific, AC charging. In case of AC charging, we have a specific or standard electrical outlet, and we can charge anywhere using this standard electrical outlet. That is one of the merits. And BMS, battery management for the battery management system to communicate, easy communication will be one of the benefits for the AC conductive charging. Coming to demerits, there is a power output limitation because the onboard charger has the limitation of size and space, because of which there is a power limitation. So this is one of the demerits. So because of this power limitation, we may not be able to charge the battery faster, right? Because of the restriction in the current magnitude, we may not be able to charge the battery faster. So that is because of the onboard charger. That is one of the demerits. So definitely it will take a larger charging time. So that is one of the demerit associated with this conductive AC charging. In conductive DC charging, we have the merits of yeah, this is one of the primary merits of this DC charging, which is no limitation on the charger size and the weight. As I already showed, that the charger is present outside the vehicle environment, so there not be any issue related to what will be the charging size and weight of the battery. Suppose if the charger has to be carried by the vehicle, then all the factors like vehicle weight and the space will come into picture. So since the charger is present outside the vehicle environment, we do not have any restriction on the charger size and the weight, because of which we have this power level flexibility and I mean high power capability. And because of this high power capability, we have this less charging time. We can able to charge the battery at faster pace, right? Coming to demerits, it has high investment cost, and then this is available only at public charging station, because we cannot incorporate this DC charging in our household appliances because it requires a lot of high power rating. So it is available only at the public charging stations. That is one of the demerits. Coming to inductive charging, which is wireless charging, that to static charging method, we have the merit of convenience, and this is more suitable for the self-driving cars, and it is safe as well. And coming to demerits, of course, the wireless charging technology is under research, so it requires a lot of a high investment cost and limitation in terms of space and weight for charging pads, and misalignment tolerance. Suppose there will be a misalignment of coils between the primary and secondary. We have to exactly align the primary and secondary coil for the efficient transfer of power from primary to the secondary. So there will be a misalignment issue present with regard to this static charging, and there will be a loss due to induction. And there is a possibility of this charger that the human has to expose in the undergo the radiation exposure, right? Coming to inductive dynamic charging, so as we already said, discussed that the primary coils are buried inside or buried underneath the road surface, and the secondary coil will be fitted in the vehicle. So the merit is that low stand-in charge time, because we don't have to wait at a particular place for charging of the battery. So low stand-in charge time and low depth of discharge. And uh, I mean, since we can charge the battery on the go, we don't have to worry about the size of the battery. So smaller battery will also do. So you don't have to worry about the location of charging station and so on. So that is one of the merits associated with this dynamic charging. And there may be some demerits, is that there may be some foreign objects present on the roads and abrasion of road surface. And because of the weight associated with the vehicle which is traveling on the road, the coil structure also changes. So these are the merits, demerits associated with the dynamic charging. Yes. So these are the various charging methods that are available, we have seen. So we will now see some of the one of the very important technique which is used in electric vehicle, which is regenerative braking. So this is one of the way of increasing the range of the electric vehicle, which is more efficient as well, because we don't have to rely on the external power source for charging the battery. Of course, the the driving range with regard to this regenerative braking is increased to 8 to 25 percentage only. But anyhow, we are without any additional energy sources, we are able to meet up this regenerative braking. So what happens in case of mechanical braking? We have this brake shoes which is pushing on this surface, so in order to stop the vehicle. So in case of mechanical braking, the kinetic energy of the wheel is simply wasted as heat energy, so which is due to the friction. What happens in case of regenerative braking is that the kinetic energy of the wheel is used to charge the battery. Okay, so in case of regenerative braking, the kinetic energy during braking, so where the way, so the vehicle will be going in some particular speed. So we'll be applying a brake. So during that time, the you know in case of mechanical braking, this kinetic energy of the wheel is simply wasted as heat. So in regenerative braking, we are utilizing this kinetic energy of the wheel, and then this kinetic energy of the wheel is converted to electrical energy to charge the battery. So this is simply achieved by switching on and off the inverter switches. For example, if you are using a AC motor drive, AC motor, electrical motor for that is used as a main drive for the electric motor. So you can simply switch off this, switch on and switch off this switches of the inverter in a proper sequence to achieve this regenerative braking. So what we are doing in regenerative braking is that simply we are boosting the back EMF of the motor. So there will be a back EMF associated with the motor, and during this braking, the back EMF of this motor will be boosted, and then this is further used to charge the battery. How this boosting is done? It is done using the internal motor inductance. This is one way, and another way, conventionally they are using this boost converters to boost this back EMF to a higher magnitude, and then and then further it is used to charge the batteries. So if you are having an inverter motor drive, we can use the same inverter for implementing this regenerative braking purpose. So further, which will use the motor inductance to boost the back EMF, and this boosted back EMF is used to charge the battery. So this driving range can be increased to a certain level without using additional energy sources. This is very important. So the energy which is going to be wasted as simply as heat is used to charge the battery. Hence the it is going to limit the cost of the system, because we are not investing on any additional energy sources. So regenerative braking is effective for frequent stop and start conditions, because if there are in urban areas where we'll be dealing with a lot of traffic, so we'll be frequently stopping the vehicle and then starting. So in that case, the regenerative braking technique will come in hand, which will be more beneficial. Also, this will be effective during downhill driving condition as well. So during downhill driving condition, if we have this regenerative braking capability in our vehicle, it is very beneficial. Right. Now, in regenerative braking, there are a lot of literatures available or research which have went. See, the idea is that there will be a back EMF in the motor. This back EMF is, we need to somehow boost this back EMF in order for the battery to charge. So this boosting previously or conventionally, I can say, it is done by the boost converter. So in the current research, in the recent research, I can say that they are using some techniques called using the motor inductance itself to boost the back EMF. So we do not need any separate boost converter for doing this. So one among this recent technology is what we call as single switch topology. there are different topologies. See, this is just a case study which is assumed that the motor is based on motor is powered by inverter drive, a three-phase inverter drive. It may be of a BLDC motor or a permanent magnet DC, permanent magnet synchronous motor, or induction motor. So any motor which is driven by a three-phase induction motor is applicable for this topology. So we will be using one of the topology which is called a single switch topology. So we will see why it is called a single switch topology. And we have other topologies like two switch and three switch topology as well. So in single switch topology, what we are basically doing is that, so here there are three legs in the inverter, I can say. So here only two legs of the inverter are shown for the simplicity of the operation, right? So this is a three-phase inverter which has three legs, and the operation is associated only with the two legs, and hence the two legs are shown here in this picture. So here uh, uh, we are just controlling a single switch, for example, and what at one particular point we are controlling only the S4 switch here. So by simply turning on and turning off this S4 switch, we can able to divert the power which is that is because of the kinetic energy that is generated because of the kinetic energy to the battery. So let us study this circuit operation in two phase. One is when the switch is on, that is in this case it is only S4. Okay, now if the S4 switch is on, what happens is that through this freewheeling diode of the S6 switch, there is a conduction path. There is a conduction path for the flow of current. So the motor inductance is used to boost the back EMF as well. So during this phase, the motor inductance of the motor is used, and the voltage is boosted, which will be done in the during switch on phase. That is when S4 is on. When S4 is on, there is a conduction path occurs. So this switch is on. So there is a flow of current in this way, and then through the body diode of this switch, the conduction takes place and it is closed. So the back of the motor is boosted by using the motor inductance. So this energy is now in the second stage, it will be transferred to the battery, which is shown on the green dotted line. As you can see here, there is a green dotted line in this image. So during the S4 switch is on, the power is stored using the motor inductance, and the stored power is then transferred to the battery using the path represented by the green dotted lines, right? So by simply controlling the switch on and off of this particular switch, we can able to achieve regenerative braking without any additional converter circuits. So this is applicable only for the motor drive, which is using a three-phase bridge uh, circuit or polytronic converter. Okay, so this is the switching pulse generation for the single switch topology. So for example, here during braking, you can see there is a back EMF, a high value of back EMF at phase A, and during that phase, you can see the switch S4 signal is activated. Switching signal, that is for S4, is activated. So during B phase, this is a duration where the back EMF is high. During that time, switching signal S6 is activated. So accordingly, you can see during the different phases, the S4, S6, and here comes the S2 is activated. So this back EMF is used to charge the is boosted using the motor inductance during this particular phase. During the switch is on, and during the switch is during the off time of the switch, then this stored energy is used to charge the battery. So this is the idea behind this. So this particular graph shows that there is a regenerative braking, that is how much energy that we can gain during regenerative braking. So this typically depends on the duty cycle of this particular switch. For example, if you are considering the S4 switching, there is a duty cycle associated with this S4 switch. So what we have done during this analysis is that we will first accelerate the motor at a constant speed. Let us say we'll take this case 307 rpm. So 307 rpm, we are just accelerating or cruising the motor at that particular speed, and at one particular instant we will be activating this regenerative braking. So during regenerative braking, what happens? The motor speed will exponentially decrease and it comes to zero. So the time during this time, what is the energy stored is calculated, which is by the battery voltage and current, and then it is plotted here. So based on the different duty cycle and based on the different speed, what we can found here is that the energy that is able to recapture during this regenerative braking will vary. Actually, it means it varies in the non-linear form. So if of course it will affects the battery stopping time as well. So this is a non-linear. So if you want to achieve the maximum energy recovery, so based on this analysis, we can be able to fix the a particular duty cycle to achieve the maximum energy recovery. Of course, it will affects on the stopping time as well. So which is further moved on to the optimization problem. If you want to have first of all, we need to give priority to the stopping time and then the possible energy recovery. So here in this case, we can design a system to get the possible energy recovery, giving priority to the stopping time. Okay, this is just an simulation result for this single switch regenerative braking topology. For this, we have considered a 40 volt 48 volt BLDC motor, power capacity of 250 watt. So this is the motoring phase. As I said, during motoring phase, the speed is it is cruised to a constant speed, and after that this regenerative braking is switched on. So it will, the motor speed will come down and it will reach to a minimum value. And during this phase, as you can see, the battery voltage is slightly increased. Okay, so hence the battery charging takes place during this voltage, and you can see the reversal of battery current as well during the regenerative braking. And this image shows the motor armature current during motoring and regenerative braking, and this is the back EMF. As the speed decreases, the back EMF is also decreases, and it will eventually end up in zero. And this is the electromagnetic torque. As we can see, during motor phase, the electromagnetic torque is positive, and during the regenerative phase, the electromagnetic torque is negative. Unfortunately, eventually comes to zero once the machine stops. Okay, so this is about a case study of regenerative braking using a single switch topology. So coming to the recent electric vehicle powertrain design, it can be designed using it can be designed for high range, and you can do some optimization in terms of powertrain components. And coming to battery, with regard to the energy, it is associated with the energy density, right? So with regard to the energy density, there are research going on with the battery technology. As of now, we are achieving this energy, that is 200 watt hour per kilogram. There are higher energy density batteries are available. It is still under research. For example, lithium air battery, lithium sulfur battery is providing high energy densities. So the research are going on this. There are these are the electric solar powered electric vehicle where solar PV is installed at the rooftop of the electric vehicle. So there are eventually there are similar to the conventional race electric vehicle, solar electric vehicle race is also going on in some countries. So the policymakers are researchers are participating in this EV event. So this is a energy flow diagram of a solar PV based electric vehicle. So here we have a unidirectional converter for implementing this MPPT, and then it is given to a bidirectional converter to stabilize, to supply power to the battery, as well as it supplies power to the motor as well. So this is bidirectional. So this is the energy flow diagram associated with the solar battery electric vehicle. And here comes the fuel cell. So we need to have a fuel storage system, and then we have a fuel cell stack. And this power generated by the fuel cell is stabilized using a power electronic converter, and then through the power is delivered to the battery, and from battery it is given to the motor. So this is how the power flow takes place, and this we have already discussed the battery swapping technology and wireless charging method. We have stationary as well as on road, and yeah, this is one of the important smart charging method and V2G, which means that incorporating the renewable energy sources into the micro grid kind of thing, and then using this renewable energy, exploiting these more renewable energy resources into the distribution network is what we call as this smart charging technology. And V2G, that is vehicle to grid communication, is also possible. Suppose during the peak requirement condition, we can supply power to the grid from our vehicle battery. So of course we can use this smart charging technology for AC charging as well as DC charging as well. And this is how this is a smart charging technology flow diagram. For charging the battery as well as we can as well as for the V2G applications. So in case of autonomous vehicle, we need to have this kind of these are the sensors like such as video camera, lidar, ultrasonics, GPS. So this autonomous vehicle will use this kind of sensors for the navigation and maneuver. Okay, coming to the conclusions. So we have known from the history that electrification is one of the most viable way to achieve this clean and efficient transportation that is crucial to for the sustainable development. So we seen that regenerative braking is effective in case of where in urban condition where frequent stop and stop condition is there, and also it is beneficial during downhill driving condition. And fuel cell based vehicles are performed for preferred for long haul vehicles due to the faster refueling and easy storage facility. And we have seen that charging electric vehicles using renewable based energy sources will help the sustainable development and leads to the pollution free environment. So with this I would like to conclude this session.
Okay, so now session is open for the query and questions, right? So if you have any query, please go ahead. Anyone? Participants, you can ask.
No question from my side, sir.
Okay. Others?
Hello, sir. This is Vinay.
Yeah.
Yes, please.
Sir, like actually, when we are speaking about different types of electric vehicles based on their powertrain or like drivetrain, we
Yes.
speak about series and parallel, right, sir?
Yes,
So
yes.
in both series and parallel, the source of charging to the battery will be from outside plug-in source.
Okay.
So, like, what is the major difference from series parallel or series parallel architecture to plug-in hybrid architecture, sir?
See, plug-in hybrid electric technology is where we can able to charge the battery using external power supply. Using external power supply, if you are able to charge the battery, this technology is called as plug-in hybrid electric vehicle. So
Yes, sir.
yes, in series hybrid electric vehicles, there is a we do not have this plug-in hybrid electric technology itself. That means we cannot charge the battery using the internal combustion engine. It will be charged.
Okay.
So
Is it like only the source of charging in series and parallel
yes,
will
yes,
be from the IC engine?
yes. So
Okay.
that is also called as range extenders in the
Huh.
literature. Yes,
Yes, sir.
because of that specific reason.
Yeah. Thank you, sir.
Thank you.
Any more question?
Good evening.
Good
Good
evening.
evening, sir.
Actually, you have discussed about this single switch charging
Yes,
topology. Okay.
yes.
So, whether this inverter VSI is inside the charger or inside the vehicle?
See, this is basically the inverter which is used to drive the motor.
Okay.
Suppose if we are having a BLDC
So it's
motor,
related with the drivetrain only.
yes.
Exactly.
The same inverter can be used for
Okay.
implementing this regenerative braking.
Yeah, that was only the question.
Yes.
Actually, otherwise 135 switches no use.
Yes.
Okay. That's fine. Thank you.
Sir, I have a question, sir.
Yes,
Yeah.
yes, Gopal.
Sir, about the microgrid that you have told here, sir, how it is connected with the electric vehicle and how we will implement it if we want to implement the microgrid with the help of the electric vehicle.
Yes, yes. So microgrid is a concept like it is smart distribution, right? So anyone can generate the power and utilize it. Suppose if you can integrate, you can also integrate the solar PV or wind farms into the microgrid,
Yes,
and
yes.
this is further used to charge the battery of electric vehicle.
So,
So
is there any optimization technique used to be with this?
There are several optimization techniques available, like to manage the power effectively from from the different sources to regulate the power. Of course, there are a lot of techniques available in the literature.
Okay, sir. Thank
Yeah.
you, sir. Thank you, sir.
Anyone else? So I have one query,
Yes, sir.
Dr.
Yes, sir.
So how will you calculate the aged energy capacity of a battery?
Okay, sir. The capacity of the battery will degrade, sir. Like as we are using for a number of cycles.
Is there any standard to calculate it? Suppose that a life of battery is 10 years.
Yes, sir.
Then after 5 years, how will you calculate the aged energy capacity of that? And capacity initially is 20 kilowatt.
Mm-hmm.
Then how will you calculate? Is there any standard formula? Is this linear or is this any specific way to calculate with that?
I'm also eager to know about that, sir. But as far as my knowledge, if you are using the more the battery is put to use for a long time. Suppose you are saying that 20 kilowatt.
Okay.
So this 20 kilowatt will further reduce to 15 or let us say 10 kilowatt hour. So that is how the degradation happens. And I would like to explore, sir. What is the
Yeah.
technique
Okay.
used for that? Yes, please.
Okay. Okay. Not an issue. Not an issue. So is there anyone having any query? Otherwise, we can close here. So if no query, then I request you all, please turn on your camera for the capturing the attendance. Then Dr. Vikram, are you there?
Yes, sir. Yes.
Yeah, so then my coordinator, Dr. Vikram, will hold the session for final wind up. Everyone, please turn on the camera. Rajesh, are you ready?
Yes, sir. I'm ready.
सब रेडी हो जाओ भाई, अटेंडेंस हो गया.
So 1 second, sir. I'm taking a screenshot. Sir, done.
Okay, thank you. Professor Vikram.
So it's my turn, sir.
Yeah, now it's your turn.
So thank you very much, my dear colleague Padma Girisan,
Thank you, sir.
for providing us with lots of introduction and working about the electric vehicle. Through the presentation, I thought I was inside the presentation only, going through the practical things, as I am very much interested in the same field and trying to work a little. So I hope the presentations has given a large area of work for the research scholars who are attending the ATAL FDP. So I thank you very much to Padma Girisan as well as Dr. Arvind Jain sir for organizing such types of ATAL FDP, and also from the department as well as NIT Agartala and the participants. I thank you, Padma Girisan, once again. Thank you, sir. So here we comes to the end of the session. So we shall leave. Good night. Bye bye.
Thank you, sir. Thank you so much.
Thank
Thank
you.
you, sir.
Thank you for the
Thank you,
knowledge.
Thank
everyone.
you. Good night.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Now, now, now we will meet tomorrow at the same time on the same day. Till then, bye.
Okay. Okay, sir. Thank you.
Thank you, everyone. Now I am closing the session.